Let's start 1 minute earlier. So I'm Han Guo from Huawei OS kernel team, and I was assigning about 11 years ago in Linaro, in the Lake team, work with Leaf, Today's topic is about the TLBI on the ARM. So we found some scalability issues, and there is a solution for that. So in case you don't know the TLBI, so what is TLBI? The TLBI is a translation local set buffer. It's a cache. It's a translation cache. So caching the mappings of the VA to the PA, is really critical for the performance. And for the TLBI, although the TLBI is a cache, but it's not the cache something like the memory. So it's without full coherency. So any update to the shared page table, software needs to maintain the coherent, which is a TLB invalidation. So any related to the page attribute and the mapping update, a TLBI will be needed. So use cases in the kernel, such as VM migration, tiered memory, and memory continuous speed, and it's a lot of more. So the picture, shows how it works, but for this part is from 86, but it shows how it works. So for the TLB broadcasting, so every TLB invalidation operation uses the following templates. The first is a DSB for the inner shareable and for only by the store, which means that ensure the priority prior page table updates has complete, and then the TLBI, which broadcasts to all the CPUs in the system, and then another DSP to wait the TLB invalidation to be complete. So from the ARM architecture, you see that the TLB will broadcast to the inner shareable or out shareable. Actually, the usually inner shareable or out shareable will include the old CPUs, even the SMUs in the system. So for typical inner shareable system, a TLBI will broadcast to old CPUs, and the DSP we just wait the TLB instruction to be retired, and that is really time consuming on multiple system. So the TLBI is really time consuming on multiple system, even especially for the ARM servers. So why? So because defined by the AMBA CHI spec, only one DVM sync can be executed at one time on the CH bus. So with the CPU number increased, the waiting list on the DM sync on the mysterious node will be increased, and leading to the delays. And on servers, it's a NUMA system. So, and the latency is added for multi-CPU die, and sometimes for the multi-CPU sockets, and which adding when you send the sync to another NUMA node and get it back, it's adding more time consuming. So especially for the which machine use cases. So if that register, the first broadcasting is set, which is set in default, which means that the DVM request from the gate source will broadcast to the older inner shareable domain, which means to the older CPUs. All of this, will introduce some scalability issues on a multiple system, especially on ARM servers. A lot of them, with around 100 cores, or even more. And here is the issue we are encountered, on the use cases running the VMs. So for the VMs, we are only run on some specific CPUs. For example, we have the focal CPU, which just runs some focal, even it's migrated to different cores. But when neighbor shared translation tables are modified, the TLBI will send to all the CPUs in the system. So take just for example, so if we run 2 VMs in 2 NUMA nodes, we just pin the vCPU on the physical CPU. So, but when the TLBI, then we are sent to all the 4 CPUs in the system. Yeah. Yeah, that's for now. And here's the test result, which on a machine. Yeah. So we test on 96 cores on server. Yeah. We put up several VMs from the 1 to 24 VMs. You know, each VM with 4 CPU cores and 8 GB memory. Yeah. Then we put up Linux in the VM running Unix bench, yeah, in the VM to test performance. In detail, you know, run 1, we put up only 1 VM with 4 CPU cores in the system. Then we run in the Unix bench to get the result. Then run 2, we put up 2 VMs, you know, then we get another result. And finally, you know, we put up 24 VMs and get the result. So we can say that it doesn't scale well from 1 to 24 VMs. Yeah, you know, TLB broadcasting is like a neighbor noise. Yeah, so I showed the picture, you know. So for 1 VM, you know, I just, you know, normalize the data from 0 to 1 to show the scalability issues, you know. So it's really not scale well, yeah. And actually, there is a lot of work related to this, yeah. Yeah, there's previous work for mitigating the TLBI overhead. So I summarized them into 2 classifications. One is reduce the TLBI times, yeah. So which means that, okay, for specific physical address or virtual address, okay, before this patch, we will send about 100 TLBI instructions. Then we can reduce that to 18% of them, 50% of them, and there's a lot of work, yeah. So actually, there are a lot of already accepted by the mainline. The first one is some avoid synchronization TLB invitation for the intermediate pitch table entries. Yeah. So that is for the navigator. It's years ago by Viediken. And another one is from the ARM v8.4, yeah, TLBI by range. So this is by Zheng. And the TLBI by range for KVM, and the batched or default TLBI showdown by Yichong Barry. Yeah. So, but to limit the TLBI broadcasting scope, no, this is not accepted by the mainline. So there is a IPR-based TLBI invalidation. Yeah, it's about 8 years ago, and there's some discussion, but not accepted by the mainline because the ARM architecture, you know, they just use the TLBI and will, you know, broadcast to all the CPUs. It's not used by the interrupt. So we still don't have a good way to limit the TLBI broadcast scope. Okay, so here is our solution. Yeah, we just, you know, to limit the TLBI by affinity. Yeah, so it's a software hardware co-design for TLBI overhead optimization. So for now, if TLBI send from one CPU in the VM, they will broadcast to all the CPU in the system. Okay, so what we have done is that we will configure the TLBI range or TLBI broadcast scope, and then if the TLBI occurs, then we send to some specific CPUs, which the VM running, and you know, which allows the TLBI executed at the EL1 to be broadcast in a configured range of physical CPUs. And how it works with hardware. So for the CPU running VMs, you know, we just introduce a per CPU call register, and to record the TLBI broadcast affinity for which CPU will run, and the software will update it accordingly. And yeah, there is some microarchitecture level updates, yeah, such as DVM broadcast. I'm a software guy, so I'm not go to in detail after those. So the key point that we just introduce a possible code register for each CPU. Then we'll record which CPU will run for this VM. Then we send those TLBI just send to those CPUs, not broadcast all the system. Yeah. And how it works for the software, is a KVM work. Yeah. KVM needs to record and update the physical CPU bitmap of the running VMs in real time. Yeah. And before each vCPU, before which each vCPU is loaded, we recalculate the VM-wide schedule CPUs. And if it's changed, we will kick all other vCPUs out and to reload the latest TLBI affinity to this register. And otherwise, we will keep it unchanged. So if when we update the register, then when we send the TLBI, the hardware will recognize, okay, I just sent to the specific CPUs, not to send to all the CPUs in the system. Yeah. Okay, here's the result. Yeah, after we do some, the code design, and this is the performance data. We did the same test on 2 machines. Yeah, one is without the TLBI by affinity, and the second one, yeah, is a new one. So yeah, from the picture, see that the blue one is that we did that before. Yeah, we don't have that TLBI by affinity, and the orange one, is with the feature TLBI by affinity. We can show that it scales well from 1 to 24 VMs, yeah, and more performance gain with CPU core added, yeah. So such as for 8 VMs, we just about 20%, and for the 16 VMs, yeah, 40, and 24 VMs about 50%, yeah. So more cost with more gains. And yeah, here's the performance data. And yeah, here's the last slide. Yeah, the to-do list. And we want to extend to the processor and the thread granularity. And yeah, to avoid the ecosystem fragment, we want to upstream to the ARM architecture. Yeah, then upstream to the mainline kernel. Yeah. That's all the contents. Yeah. Any questions? Okay. Yeah. Thank you.